This is Akashavani Mangalore. Dear listeners, in today's Talk in English program now, Emmanuel Deepak De Silva, Assistant Professor, Postgraduate Department of Physics, St. Aloysius College, Mangalore, will speak on the topic Ionizing Radiation.
August 6 and 9, 1945, the atomic bombs dropped on Hiroshima and Nagasaki during World War II released a massive amount of energy, causing widespread destruction and immediate casualties. The primary sources of radiation in these events were gamma rays and neutrons resulting from nuclear fission reactions. The intense radiation exposure led to acute symptoms such as burns, radiation sickness, and death. Survivors experienced long-term health effects, including an increased risk of cancer, particularly leukemia and solid tumors. March 11, 2011, the Fukushima Daiichi nuclear power plant in Japan experienced a severe accident following a massive earthquake and tsunami. The incident led to the release of radioactive materials including iodine-131, cesium-137, and strontium-90. The release of radioactive materials into the environment had significant consequences. Contaminated water, soil, and air pose health risk to the local population. Residents were evacuated from the affected areas to minimize exposure. The incident highlighted the importance of effective emergency response and the potential dangers associated with nuclear power. If radioactive sources are not used wisely, there can be several harmful consequences. Uncontrolled exposure to radiation can lead to various health issues, including acute radiation sickness, long-term radiation effects, and an increased risk of cancer. Improper handling or disposal of radioactive material can result in contamination of air, water, and soil, affecting ecosystems and wildlife. High levels of radiation can cause mutations in the DNA, potentially leading to hereditary effects and genetic disorders in future generations. Chronic exposure to low levels of radiation over an extended period of time can increase the risk of cancer and other health problems. Radiation can be harmful to living organisms due to its ionizing nature, which means it has enough energy to remove tightly bound electrons from atoms, leading to the formation of charged particles. This can result in damage to biological tissues and genetic material. There are different types of ionizing radiation, including alpha particles, beta particles, and gamma rays, each with varying levels of energy and penetration. If we consider the atom, the nucleus is the center of the atom, where approximately all of the atom's mass is concentrated. Subatomic particles like protons and neutrons form the nucleus. We have on our planet certain natural elements that are unstable. As a result, their nuclei disintegrate and emit radiation, releasing energy. The emitted energetic radiation is called ionizing radiation. The phenomenon of disintegration or decay of the nucleus of an atom emitting radiation is referred to as radioactivity, and the element is called a radioactive element or radionuclide. The rate of radioactive disintegration or decay of the radionuclide is measured in becquerels. 1 becquerel corresponds to 1 disintegration per second. Radioactivity is not a new phenomenon on our planet. It has always existed. Naturally occurring radioactive elements can be found in the earth crust, our food and drink, and the floors and walls of our offices, homes, and schools. Radioactive gases are present in the air we breathe. Our own body's muscles, bones, and tissue contain naturally occurring radioactive elements. Man has always been exposed to natural radiation, both from within and without the planet. The radiation we get from space is referred to as cosmic radiation or cosmic rays. Example of some of the natural radioactive elements are uranium, thorium, radium, etc. Man-made radiation such as X-rays used in cancer therapy and disease detection exposes us to radiation as well. Radiation from nuclear power plants fallout from nuclear explosive testing, and trace amounts of radioactive elements discharged into the environment by coal and nuclear power plants all expose humans to radiation. Other consumer products such as luminized wristwatches, ionization smoke detectors, and so on are other sources of radiation exposure. Radionuclides decay at a known rate regardless of environmental influences such as temperature or pressure. The half-life of a radionuclide is the amount of time it takes for half of it to decay or disintegrate. This half-life varies by radio element and can range from billions of years to fractions of a second. For example, uranium-238 has a half-life of 4.5 billion years, but iodine-131 has a half-life of 8 days. Potassium-40, the principal cause of radioactivity in our bodies, has a half-life of 1.42 billion years. Now, we are looking into what the types of radiation are. The term radiation is very broad and includes such things as light and radio waves. In our context, the term ionizing radiation refers to radiation that can cause material to become electrically charged or ionized when it can pass through material. Radiation-induced electrical ions in living tissues have the potential to interfere with regular biological functions. There are various types of radiation, each having different characteristics. The common ionizing radiations generally talked about are alpha radiation. Alpha radiation can be stopped completely by a sheet of paper or by the thin surface layer of our skin. However, if alpha-emitting materials are taken into the body by breathing, eating, or drinking, they can expose internal tissues directly and may therefore cause biological damage. Beta radiation consists of electrons. They are more penetrating than alpha particles and can pass through 1 to 2 centimeters of water. In general, a sheet of aluminium a few millimeters thick will stop beta radiation. Gamma rays are electromagnetic radiation similar to X-rays, light, and radio waves. Gamma rays, depending on their energy, can pass right through the human body but can be stopped by thick walls of concrete or lead. Neutrons are uncharged particles and do not produce ionization directly, but their interaction with the atoms of matter can give rise to alpha, beta, gamma, or X-rays, which then produce ionization. Neutrons are penetrating and can be stopped only by thick masses of concrete, water, or paraffin. Although we cannot see or feel the presence of radiation, it can be detected and measured in the most minute quantities with quite simple radiation measuring instruments. Naturally, the question arises, how can we detect and measure radiation? Sunlight feels warm because our body absorbs the infrared rays it contains. But infrared rays do not produce ionization in body tissue. In contrast, ionizing radiation can impair the normal functioning of the cells or even kill them. The biological effects of ionizing radiation vary with the type and energy of the radiation. A measure of biological harm or risk is related to the dose of radiation that the tissue receives. The radiation dose absorbed is measured by a unit called sievert. Since 1 sievert is a large quantity, radiation doses normally encountered are expressed in millisievert or microsievert, which are 1000 or 1 millionth of a sievert. For example, one chest X-ray will give about 0.2 millisievert of radiation dose. Our annual radiation exposure from all natural sources is roughly 2.4 millisieverts on average, while actual exposure might vary by several 100% based on one's geographic location. Travelers by air thereby increase their risk of radiation exposure from cosmic rays, which is largely based on altitude and somewhat depends on latitude. Now we will see if there are any protocols in place regarding radiation protection. It has long been known that ionizing radiation can harm human tissues at high dosages. Over the years, scientists have become increasingly concerned about the potentially damaging effects of exposure to large doses of radiation. As a result, a autonomous non-governmental organization of specialists in the domain, the International X-ray and Radiation Protection Committee, was founded in 1928. Afterwards, it was renamed as International Commission on Radiological Protection (ICRP). Its goal is to lay out fundamental guidelines of radiation protection and provide suggestions in this regard. The International Atomic Energy Agency (IAEA) publishes basic safety standards for radiation protection, which includes radiation protection guidelines provided by the ICRP. In 1955, the United Nations General Assembly established the UN Scientific Committee on the Effects of Atomic Radiation, which is an intergovernmental entity. The goal of this committee is to gather, examine, and share data on environmental radioactivity and ionizing radiation levels, as well as the impacts of these radiations on people and the environment. Basic approaches to radiation protection are consistent all over the world. The ICRP recommends that any exposure above the natural background radiation should be kept as low as reasonably achievable but below the individual dose limits. The individual dose limit for radiation workers averaged over 5 years is 100 millisievert, and for members of the general public it is 1 millisievert per year. The effects of radiation at high doses and dose rates are reasonably well documented. A very large dose delivered to the whole body over a short period of time will result in the death of the exposed person within days. Much has been learned by studying the health records of the survivors of bombing of Hiroshima and Nagasaki. The research demonstrated a clear dose-response relationship, meaning that higher doses of radiation were associated with higher risk of adverse health effects. The study did not find significant evidence of hereditary genetic effects in the children of survivors. However, regarding low doses of radiation, there is still considerable uncertainty about the overall effects. It is presumed that exposure to radiation, even at the levels of natural background, may involve some additional risk of cancer. However, this has yet to be established. Radioactive elements can have beneficial uses in various fields including medicine, industry, and energy production. Radioactive isotopes are used in medical imaging techniques such as positron emission tomography scans and single photon emission computed tomography scans for diagnosing and monitoring diseases. Radiation therapy, which uses controlled doses of radiation to target and destroy cancer cells, is a common treatment for various types of cancer. Radioactive sources are employed for non-destructive testing in industries, ensuring the integrity of materials without causing damage. Radioactive sources are used to measure the thickness of materials in industries like manufacturing and construction. Nuclear power plants generate electricity through controlled nuclear reactions. Nuclear power is a low-carbon energy source that can help mitigate climate change. Radioactive sources can be used for irradiating food to kill bacteria and pests, extending the shelf life of certain products. Radioactive tracers help scientists track the movement of substances in the environment, providing valuable data for research and monitoring. To ensure that the benefits of radioactive elements outweigh potential harms, it's crucial to implement rigorous safety measures, robust emergency response plans, regulatory frameworks, and waste management practices. Strict adherence to safety protocols in nuclear facilities, responsible handling of radioactive materials, and ongoing research into safer technologies contribute to minimizing risk. It is also important to remain informed about advancements in nuclear science and technology as researchers continually work towards enhancing the positive applications of radioactive elements while minimizing potential negative impacts. public awareness and education play a key role in fostering a balanced understanding of the risk and benefits associated with the use of radioactive materials. No human activity or practice is totally devoid of associated risk. Radiation should be viewed from the perspective that the benefit is greater to mankind than the associated little manageable risk.
Dear listeners, that was the talk Ionizing Radiation, delivered by Emmanuel Deepak De Silva. The talk came to you from the studios of Akashvani Mangalore.